So before we jump into the talk, as a reminder, this is being recorded, and also the SOFIA archival call is still open, so feel free to look at that. But today we have Collin Knight from UWO, who's going to be talking about using SOFIA to connect astronomical polycyclic aromatic hydrocarbons to their physical environment, conditions, event date. Environment and conditions. All right, so Collin, take it away.
Okay, so hopefully you can see my mouse cursor.
Yep.
Okay, perfect. Okay, so my name is Collin Knight. I am a postgraduate researcher working at the University of Western Ontario with Professor Els Peters. And we primarily research astronomical PAHs, or polycyclic aromatic hydrocarbons. And my research is focused on connecting polycyclic aromatic hydrocarbons and their corresponding mid-infrared emission with the environmental conditions in which they're found. And we found SOFIA to be instrumental in helping us achieve this goal. So the first part, I want to just give kind of a general background about PAHs within the interstellar medium. So I just talked about like the general structure, mid-infrared emission that we attribute to PAHs, and how this emission varies spatially. So first, just a brief overview of the dust life cycle. I mentioned the dust life cycle because PAHs are typically thought of it being the short wavelength range, or the small end of the dust continuum. So PAHs and dust form in much a similar way. So typically you have dust formation in the outflows of low to intermediate mass loss of AGB stars. And this dust is distributed throughout the ISM, which can be further processed and enriched through processes such as shock waves from supernova of massive stars. And this can cause other processes to happen in the dust, such as fragmentation or destruction, to give rise to smaller species, such as even interstellar PAHs. Furthermore, the cycle can use, you get star formation from compressions in giant nuclear clouds, and that gives rise to next generation of star formation and stellar systems, where dust get locked in primitive bodies such as meteorites, planets, asteroids, comets, etc. And these stars age, and you get back to this first point of the cycle, and we get continued production of dust and enrichment of the ISM. So with that in mind, our research primarily focuses on mid-infrared astronomical spectrum. It's found throughout the interstellar medium of the Milky Way and extragalactic sources. So these type of galactic sources include H2 regions, post-AGB stars, young stellar objects, planetary nebula, reflection nebula, the diffuse ISM, and galaxies as a whole. So here's the external galaxy M81. Here it is in the optical, which it shows nice spiral arms. If you look at it in the mid-infrared, you see that it's basically bright everywhere you have optical emission, and this is in large part attributed to these mid-infrared dominant bands, which are at 3.3, 6.2, 7.7, 8.6, 11.2, and 12.7 micrometers. And here's a spectrum of the Orion bar, a very well-studied galactic source. And so these bands are typically attributed to stretching and bending modes between the carbon and hydrogen constituents of PAH molecules. And so these bands are perched on top of a rising dust continuum, and we also have these underlying plateaus, which are also attributed to species that are related to PAHs or aromatic in nature. And I'd also like to note that the 7.7 band here can also be broken into two kind of major components at 7.6 and 7.8. So what are polycyclic aromatic hydrocarbons, or PAHs, exactly? Well, they form from the fundamental aromatic unit, a benzene ring, where you have basically 6 carbon atoms in a hexagonal configuration, where they basically share their electrons in a delocalized pi bond, making them much more stable than aliphatic or linear carbohydrates, or sorry, hydrocarbons. So building from a single aromatic unit, you can get these into larger and larger planar structures of a hexagonal units, with hydrogen atoms located on the periphery. And here I give a couple examples of simple PAHs and a related species, as we'll see later, fullerenes, which are also formed from the same kind of aromatic material. So PAHs can also be found on Earth. They're highly carcinogenic. They're a family of molecules. They exist in many different soothing products, such as soot from factory plumes, cigarette smoke, auto exhaust, and charcoal, among other things. So they're very common on Earth as well as the interstellar medium. So now that we know what PAHs are, why do we think we can call these the carriers of these mid-infrared bands? The reason we attribute these to PAHs is due to primarily a couple of studies in the 80s. First off, Amendola and all in 1985, they looked at spectrum from autosoot and found the same kind of prominent bands at 7.7 and 6.2 as they found in the Orion bar mission. So this indicates that the carriers of these bands are aromatic in nature. Additionally, another study was done in the 80s by Chris Selgren in 1984, where they looked at near-infrared continuum emission observations within our reflection nebula, and found that the observed color temperature was found to be independent of the distance from the illuminating star. Now, classical dust grains of 1 micrometer in size, they're within thermal equilibrium with their surroundings, and they don't become hot enough to kind of account for this continuum emission. So instead, a model was used to explain this of a single UV photon absorption event of large molecules of about, let's say, 10 angstrom in size, from about 50 to 100 carbon atoms. And so these molecules are electronically excited, and this energy is rapidly redistributed into vibrational modes between the carbon and hydrogen constituents, and this is then emitted in infrared light in terms of these mid-infrared bands that we detect throughout the interstellar medium. So other than the fact that we just detect them everywhere within our galaxy and other galaxies, why are these bands astronomically significant? Well, they account for up to 20 to even 30% of the infrared emission in galaxies. They've been found to account for 10% of the cosmic carbon inventory. They play an important role in many different processes in the ISM, such as the heating of the neutral ISM from photoelectric ejection, as well as the ionization balance in neutral ISM from photoionization and recombination processes. Additionally, their large surface area provides an ideal site for surface chemistries for the formation of molecules such as H2 or CO, etc. Additionally, they've been found to be used as tracers for star formation in external galaxies. And other studies have shown that their large surface area may allow them to be a catalyst for formation of prebiotic molecules in ices on cometary or asteroid bodies. And these molecules include amino acids and amphiphilic molecules that are found in cell membranes. So there are multiple reasons that we would like to better understand these PAH emission and why they are, or how they are connected to their environment. So these emission bands aren't static. They vary spatially within the sources and in between sources. But generally, you can kind of break them into 2 major groupings based on the ionization state, so the PAH charge. Essentially, the bands that you find at 62, 77, and 86 are all very well correlated, and they're found to be attributed to ionic pause, whereas the 3,3 and the 11,2 are also well correlated, but they are more predominant in neutral pause species. Additionally, variation in PAH emission can provide further insight into other properties of these molecules, such as the average size or the overall edge structure of these molecules. So these molecules are primarily found within photodissociation regions or photodominated regions, PDRs. So these are regions defined to be where the far ultraviolet photon flux has energies between 6 and 13.6 electron volts, which controls the physics and gas or chemistry of the gas. This includes all the atomic and at least 90% of the molecular gas in the galaxy. And here we present a simple 1D model of a PDR. So you have a young massive star, say an O or a B-type star. They have a strong UV flux, and they're surrounded by an ionized H2 region or a cavity. And this UV flux is incident on a molecular cloud, which the PDR is kind of the thin inner layer of the molecular cloud that gets irradiated by this UV flux. And you can break this into multiple domains with increasing cloud depth. So the PDR is defined beginning at the ionization front, where you have a transition from ionized hydrogen to atomic hydrogen. And you get, going in further, you have the transition from atomic to molecular hydrogen, and furthermore into further depths, the transition between ionized carbon to molecular carbon monoxide. And finally, the PDR ends at the transition between atomic and molecular oxygen, at which point you move into the molecular cloud domain. So typically when we talk about PAH emission, we're talking about PAH emission coming from PDRs. However, we also find that this emission varies spatially within extended galactic sources. So for instance, the very well studied reflection nebula NGC 1723, we find a stratification of emission from components that are related to PAHs. So here I introduce another component called very small grains. They're typically related to PAHs in that they are expected to have aromatic kind of subunits as well, but they are larger in nature, so maybe up to about 1,000 carbon atoms and 10 nanometers in size. So very small grains kind of peak at the molecular cloud or PDR front region, and as you move closer and closer to the illuminating source, you find prominent emission from neutral PAHs, shown in green, and further inwards you get more emission from ionic PAHs, and moving closer and closer to the star, you find that the PAH abundance is found to decrease, whereas you also find an increase in emission from C60 or Buckminster fullerene. So these authors have taken this to suggest that the destruction or isomerization of large PAHs may result in the formation of these fullerene molecules. Additionally, another study was done of the reflection of the NGC 2023 by Peters and al. In 2017, where they found that these individual mid-infrared bands also peak at different distances from the illuminating source within this nebula. So this is indicative of the photochemical evolution of these species that's been being driven by increasing exposure to the UV field of the star. So if you kind of look at this diagram, within a molecular cloud region, you have larger plot clusters or very small grains. Moving inwards, you have kind of more larger regular PAHs. And at the PDR front, you have neutral PAHs. Moving inwards, you have a transition into more ionic PAHs. And finally, this gives rise to the formation of fullerenes. So as I mentioned before, variations in these band strengths can be used to trace changes in the overarching molecular properties of these PAH populations, such as the charge state, the average size, and the edge structure. For instance, another study looking at IGC 2023, we looked at a radial line extending from across this southern PDR, going towards this illuminating source HD 37903. We found that the PAH size, as traced by the 11.2/33 band, increases going from the PDR front towards the star. So what that indicates is that you have, again, UV processing of these species where the smaller PAH species are destroyed and only the largest PAHs can exist closer and closer towards the illuminating source. And so for this study in particular, we used flight cam observations to measure the 3.3 band, and we used IRAS short high to measure the 11.2 band. So moving onwards, motivation for my studies that I'll talk about today is we want to talk about how PAH properties are very dependent on the physical environment, and how can we use PAH emission to kind of trace physical conditions in the host environment. So when I talk about physical conditions, I'm talking about the radiation field, the gas density, the gas temperature, etc. So if we can characterize the relationship between PAH emission and these physical conditions, this will be extremely useful to the astronomical community moving forwards, with the upcoming influx of mid-infrared data expected to be obtained by the James Webb Space Telescope. So overall, there have been some interesting studies in the recent decade, basically connecting the empirical relationships between PAH emission and the for ultraviolet radiation strength, or G0. So these authors, Stock and Peters, they looked at the ratio of the two components of the 7.7 band, so the G7.8 and the G7.6, and they found that with increasing radiation field strength, this ratio decreases. So they have a fairly convincing correlations found based on integrated spectrum of a wide variety of galactic sources. However, you can see that the low G0 range is poorly populated, and this relation can change even with additional points at very low radiation field strength. So one of our goals is to kind of get more data to kind of better populate this entire parameter space and further constrain this relationship. Additionally, Galliano et al. In 2008, among other authors, found a strong correlation between the 6.2 and the 11.2 PAH emission bands. So if you recall, the 6.2 band was attributed to ionic PAHs, and the 11.2 band was attributed to neutral PAHs. And we have what's called gamma, or the ionization parameter, which is a combination of physical conditions such as the radiation field strength, the gas temperature, and the electron density. And there's a strong correlation found within these galactic sources, probing a wide range of ionization parameter strength. So, with these relationships in mind, we want to kind of look at this in more detail in a more spatially resolved sense. So we want to measure these PDR conditions not for an integrated source, but spatially within extended sources, and compare it to spatially resolved PAH emission. So to do this, we want to cover the full range of parameter space in G0, or far ultraviolet radiation field strength, and the gas density. So as you've seen with the first relation we presented, we need to kind of look at the lower G0 range as well. So for the mid-infrared emission, we'll rely on Spitzer observations for now. But for the PDR, to derive measurements of these PDR conditions, we employ PDR models. So these PDR models make assumptions about the gas phase abundances and the dust gain properties to predict the dominant and atomic and molecular species as a function of cloud depth, and the dominant cooling lines as a function of cloud depth and gas temperature. So these far-infrared cooling lines are far-infrared recombination lines that are optically thin. They radiate energy away from the cloud, basically cooling the glass, or the gas, excuse me. And these lines have different abundances with respect to cloud depth. And so we want to measure these cooling lines by employing SOFIA instruments such as PPLS. And we'll use these cooling lines as input into PDR models to derive spatially resolved maps of G0 or far ultraviolet radiation field strength and the gas density and temperature. So in part 2, I want to move on to talking about my study of the reflection nebula NGC 133. So our goal is to kind of characterize the PAH emission as well as the physical conditions within this nebula and see if there's any kind of real variations between the irradiated PDR and the diffuse ISM surrounding the source. So for our observations, we have multiple observations in the mid-infrared and the far-infrared. We used Spitzer IRAS short-low to map the PAH emission. And we used SOFIA PPLS to measure the far-infrared cooling lines at 63, 145, and 158 micrometers. And additionally, we have observations of from Herschel packs at 70, 100, and 160 micrometers to map the far-infrared dust continuum. So taking all these observations into account, we'll be able to compare PAHs and their physical conditions. But first, I want to talk a little bit about the spatial distribution of the PAH emission. If you look at the ionic and neutral spatial distributions, we find that in comparison, the PAH ions are much more compact and compared to the neutrals, which have a much more elongated shape moving away from the nebula. But generally, both bands tend to peak south of the primary illuminating source in this nebula, SVS3. So as I mentioned earlier, we want to look at how does PAH emission change with respect to different interstellar environments. So within our IRAS aperture, we have two different interstellar environments. So we have the diffuse ISM of kind of low radiation field strength and low gas density, and we have a more highly irradiated nebula. So here I show some significant correlations between PAH emission bands within this nebula, and we color code them by the 7.7 band. And if we look at correlations within the nebula, we find that they're much more tightly correlated within the nebula in comparison to the diffuse ISM surrounding the nebula. So this indicates that there's kind of some distinct PAH emission happening within the nebula and the diffuse ISM surrounding the nebula. And particularly, you can kind of see like a branching here between the 6.2 and the 8.6 band, as well as this kind of strange kind of arcing behavior with the 6.2 and the 12.7 band. So when we look at even more correlations, color-coded by the 8.6 over 11.2 PAH ratio, we kind of break this up into kind of three different subregions. So the nebula, the transition region between the nebula and the diffuse ISM, shown in cyan, and finally the diffuse ISM. So if we look at the plateau underneath the 6 to 9 PAH features and compare it with the 6.2 or 11.2 ratio, we find this kind of a bilinear trend, which shows two distinct relations between these parameters, between the nebula and the diffuse ISM. And if you look at the subcomponent of the 7.7 band, so the G7.8 component, and a subcomponent of the 8.6 band, the G8.6, we find even three distinct kind of relations with respect to this correlation plot. And these can be related to different spatial regimes within our aperture. And so our explanation for this is that some of these PAH bands may be due to multiple PAH subpopulations, in particular the 6.2 and the 7.7 band. And what I mean by PAH subpopulation is populations of PAHs that are characterized by different overall PAH properties, such as charge states, average sizes, and overall kind of structures. So there's kind of two distinct regimes here, and we want to kind of see how that relates to our physical conditions, in which we'll map next. So to characterize the far-infrared dust emission, we do some far-infrared SED fitting of a black body of the form shown here. And so we use our PAX data at 70, 100, and 160 and integrate under the curve to derive the far-infrared dust emission, which has a, again, a very kind of concentric distribution spatially with a peak south of the star as well. So it's kind of similar in that respect to the PAH emission distribution that we've seen earlier. So for our PDR cooling lines, we have three different cooling lines mapped with the SOFIA FEFLS. And again, all these bands kind of show kind of concentric distributions peaking around the illuminating source. So now that we have all the ingredients to derive the far-infrared, or the sort of the physical conditions, we input this into PDR models. So we get a simple estimate for the far ultraviolet radiation field strength from the far-infrared dust continuum, basically a linear relationship here. So we have a G0 map basically identical in the spatial distribution to our far-infrared dust continuum map. And it typically peaks at 3 times 10 to the 3 times the interstellar medium value, or in the Having field. So combining this with the far-infrared cooling lines, we're able to derive maps for gas density and temperature by employing PDR models from the PDR toolbox from the University of Maryland. So we combine these parameters to get a map for the ionization parameter, which is shown here. Again, has a very kind of concentric morphology peaking to the south of the source. So next we put this all together and we compare emission from PAHs with respect to the PDR diagnostics, or the PDR conditions. And we find that band ratios between 6 to 9 micrometers, so, and here we show the 6 to 11.2, show a correlation with respect to the G0 and the diffuse outskirts. But when we go into the irradiated nebula, we find that there's much more scatter, which may be due to the geometry of the source. Likewise, we're able to produce the, tight anticorrelation between the G7.8, the G7.6 components and G0 as found in Stock and Peters. But again, note the kind of steeper slope found here with respect to the previously derived relations. Additionally, we find a novel anti-correlation between the G8.6 and G7.6 subcomponents and the radiation field strength, which we think may be suggestive of photoprocessing of larger compact to smaller compact PAHs with higher exposure to the UV radiation fields. Unexpectedly, we didn't find any strong relations between the ionization parameter and any kind of PAH ratios, as was found by Galliano et al. In 2008. with the exception of a weak correlation found between G86 and G76 and gamma. But I would take this with a grain of salt because we cover such a small range within this ratio. So more work needs to be done in kind of constraining this relation. So from this study, we can conclude that the PAH bands, so the ionic PAHs and neutral PAHs, show two distinct spatial morphologies within the reflection nebula NGC 133. We find bilinear relationships between multiple emissions features within this nebula and the diffuse ISM, which we think can be attributed to multiple PAH subpopulations comprised of different kind of properties within the populations. And finally, we're able to find empirical relationships between a wide variety of PAH emission ratios and the far ultraviolet radiation field strength, but unexpectedly, we do not find anything with respect to the ionization parameter gamma. So how am I doing with the time, Steve?
Yeah, you did well. We still have some time for questions.
Oh, I still have a few sections. I just want to make sure I have some time. Okay, thank you. So in the next part, I would like to present some preliminary results, much in the same vein as the previous section, where we compare PAH emission and PDR conditions within a ultra-compact star-forming region, IRAS 12063. So again, we have a set of observations in the mid-infrared and the far-infrared, which are all spatially resolved. So we have FIR observations tracing the 63, the 145, and 158 cooling lines, shown with these respective apertures. And again, we use Spitzer IRAS short-low spectra cubes to trace the PAH emission. And finally, not shown here, we use the Herschel PAX 70 and 160 photometric observations to trace the far-infrared dust continuum. And so this source is characterized by two ultra-compact regions, which are traced in the radio as source A and source B. And so we have kind of the relevant PAH ratio maps from this previous section. And again, we kind of show the significant PAH band spatial distributions. So in terms of the ions and the neutrals in 7.7 and 11.2, which seem to have a very similar kind of distribution, which kind of peaks around this source A. But as you can see, in terms of these individual PAH ratios, we have a very kind of different picture with peaks kind of far away from the source center. So likewise, we use our PAX observations to, again, derive the far-infrared dust emission from SED fitting. So this far-infrared dust emission is found to kind of peak to the slightly to the west of the ultra-compact regions. And finally, we have far-infrared cooling lines at 63, 146, and 158, all shown at their native resolutions, which are typically concentric distributions peaking near the sources, or peaking near the central source. But as you can see, there's kind of a slight offset between the 63 and 158. So in the FIFI blue and red channels. So again, we combine the far-infrared cooling lines and far-infrared dust emission in these PDR models using the PDR toolbox software. And we're able to derive maps for the radiation field strength, the gas density, gas temperature, as well as the radiation field, or the ionization parameter, excuse me. So what you can see here in terms of the distribution for the radiation field is it peaks at about 10 to the 4 times interstellar value, which is well in agreement with previous literature values. However, in terms of gamma, we kind of get this very astronomical distribution, which peaks far to the west of the source center. And so we're not really sure at this point why we get such an odd distribution for gamma. However, we do have some preliminary correlation results to present. So as you can see here, when we look at this ultra-compact star-forming region, we're able to reproduce the similar correlation with respect to G naught, as was found in the reflection nebula 133. However, we don't have any strong correlations found with respect to gamma, so we kind of need to revisit our models a little bit and see if we can kind of come up with a physical explanation as to why our PAH observations and our ionization parameter observations don't really match up. So hopefully we'll be able to share this work with the community in a wider sense when we publish it later this year. But for now, this is how far we have. But the main conclusion is that we can kind of see that these empirical relations kind of hold for a wide variety of sources. So to conclude, the main conclusions from this talk that I hope you will take away is that PAH emission characteristics in terms of the band strengths, as well as other properties, depend on the astronomical environments in which they're found. So the diffuse ISM, irradiated PDRs, and highly irradiated ionized H2 regions all tend to show different kind of correlations between PAH ratios and their physical environments. SOFIA observations, including from FIFLS and GREAT, will be instrumental in mapping the far-infrared cooling lines, which we employed here and hope to employ in the future to derive novel spatially resolved PDR environment measurements. And I hope I convince you from these few sources that PAHs and their respective emission components have much potential to be used as PDR diagnostics in future studies. So for future work, we're also applying the similar analysis that was done for NGC 133 and IRAS 12063 for the star-forming region W49A, which is comprised of many different ultra-compact H2 regions and is often considered to be the galactic analog of star-forming galaxies. So that will be instrumental in allowing us to kind of perhaps extend our spatially resolved relations to use them as a tracer for PDR diagnostics in galactic studies. As you may expect, JWST will be a game changer for PAH research, as we have much higher spatial resolution and higher sensitivity than the current generation of space-based mid-infrared facilities. Additionally, it will include all the major PAH bands, particularly the 3.3 band, which you may have noted that I omitted from part 2 and part 3, as the Spitzer IRAS short-low Spectra does not include the 3.3. And in fact, we relied on other instruments such as FlightCam in the past to actually map this 3.3 band. So our ultimate goal is to compile a database of PAH emission and far-infrared derived PDR conditions to critically test PAHs as PDR diagnostics over the full range and parameter space of far ultraviolet radiation field and gas density. And hopefully that will be useful going forward when we get more mid-infrared data from JWST, SOFIA, and other future mid-infrared studies. And in that sense, SOFIA will continue to be instrumental with observations from FIFLS and GREAT to measure these far-infrared lines in the near future. So with that, I thank you very much for your attention, and I will be happy to take any questions that you may have about this talk. Thank you.
Thanks, Collin. That was great.
Thank you.
All right, we have some time for some questions. Feel free to either unmute or raise your hand or link them in the chat.
This is Eric Becklin. Good summary talk. I first wanted to mention another source that I know has PAH emission at 3 microns that Sarah Loggins did for her thesis is W3. I would put that on the list of objects that you might want to look at. W3A.
W3A?
Yeah, it's a very nice region to study because it separates out like the Orion bar, but it's in a circle around the exciting O stars.
Okay, so it's more of a based on morphology.
Yes.
Okay.
Yeah. So the geometry is fairly well known. And she never really finished the analysis. And I don't know how much of the longer wavelength PAH has been done.
Okay.
There's some that exists.
Well, we'll have to definitely look at that paper, and it would definitely be an excellent source to further our database.
Yeah. Well, look at it and try to get her thesis at UCLA.
Sorry, what is her name again?
Sarah Loggins.
Sarah Loggins. Okay.
She's on the PAH papers with myself and Ian McLean and
Okay.
Aaron Smith.
Okay, I would be sure to check that out.
Yeah. And with regard to the sources you talked about today, how do they vary, say, relative to Orion in terms of distance and the amount of ultraviolet flux, or what's the exciting sources?
That's a very good point. So Orion, the Orion bar, or Orion in general, is thought to be about 400 parsecs away.
Yeah.
So IRAS 12063 is about 10 kiloparsecs. So it's much farther away.
Yeah. Okay.
Likewise, W49, which we'll be looking at, is also about 10
that's yes, similar. Yeah.
NGC 133 is, I think, maybe about 100 to 200 parsecs. So it's actually comparable in distance.
Okay. Yeah. So you're looking at, and how about in terms of the exciting sources?
So Orion, I think, is probably within the same. So if you'll allow me to go back to the figure I showed earlier. Excuse me. So Orion is right here, and it's kind of comparable with IRAS.
Use your Orion. Where is it?
Orion is about here, I would think.
Okay. And where is 133? Is it on there?
133 is probably a little bit in the same region as 2023 and 7023.
Okay, it's up near the B stars then.
Yeah, it's an intermediate regime.
Yeah. Okay. Yeah.
All right, do we have any other questions? We don't. I have one, Collin. If you could go to slide 30.
Yes. Okay.
Sorry, 29.
29.
Yes, the fact that you don't see much of a correlation in this, and there was a previous work that did, was the previous work looking at a similar system or this system in particular?
So the previous work that I cited actually looked at the Orion bar, which was done by Galileo in 2008. So one reason for this may be the fact that we have more of a face-on morphology. So you kind of get a more of a wide range in geometries that you're tracing in terms of PDRs, whereas the Orion bar has kind of a nice edge-on morphology. We actually did a study on the Orion bar where we kind of found that we were able to reproduce the correlations from Galileo and Renal with respect to the newer Spitzer data. However, yeah, we're still kind of perplexed about why we don't really reproduce those nice correlations found within the bar.
Could it be related to unique conditions of the ISM in those two environments, or are they expected to be pretty similar?
So this reflection nebula has probably a radiation field strength on an order of magnitude lower than the Orion bar. So it could be due to, yeah, a different morphology, different kind of physical conditions. What's interesting is that you do kind of see kind of a higher kind of concentrations and points down here, kind of suggesting that you know, there is some kind of relationship with morphology or kind of general spatial distribution of these bands. So hoping to kind of look into these models in more detail and see if we can kind of uncover why we don't get the correlations that we expect with respect to gamma. And hopefully we can resolve it in our studies of these ultra-compact star-forming regions.
Could the correlation found in the higher intensity radiation be linked to some kind of like PAH formation sequence? This is a little outside of my depth here, but is that something that you could try to figure out?
Yeah, potentially. If we have, I mean, if we have all the bands, we could kind of get a spatial sequence of these bands, like with some for 2023, and see how it relates to, say, it could be due to formation or it could be due to processing closer to the star. There are multiple factors that, honestly, we're not quite sure, but hopefully with more sources and more data, we can kind of weed out the reasons as to why we don't get as strong a correlation as we expected.
Yeah, it's really interesting. All right, any other questions? All right, well, thank you so much for your time, Collin. We really appreciate it. Great talk.